Hi, everybody. My name is Debbie Brisbane, and we're going to be talking today about how to use a concrete wall design in Risa. Today's webinar will go through a lot of different topics here. We're going to talk a little bit about how the code applies. We're going to talk about how to use this feature inside of Risa, and we'll try to hit a lot of different points. In particular, we're going to jump into two programs that we've got here, Risa Floor 5.1 and Risa 3D 9.1. These two versions are the latest versions we just released about a month ago, and you should have, if you're up to date with the maintenance packages here, you should be getting that in the mail any day or have already received it. And this concrete wall feature is going to be brand new with inside of that version there. So first of all, let's jump into some of the code information. We're going to be talking about ACI 318.05 and ACI 318.08. Those are the two references that we implemented this concrete wall for. So you're going to want to make sure that you have your code set to that version of the code in order to get the wall feature. In particular here, oops, I'm going to jump here. Looks like in particular here, sorry, jumped to the wrong thing. We're going to make sure we click here. Oh, there we go. What sections of the ACI apply to walls? And what we're going to be saying here is that we're actually applying, let me close this out here, make sure we're seeing this. We're going to be applying this to certain sections of the code. And we actually have a lot of different sections, but I'm going to focus on some of the main ones here. Section 7.6 in the ACI, and I'm referencing 08 for reference if you wanted to check the code there. The general reinforcement spacing requirements, you can see some minimums and maximums at 7.61 and 7.65. You've also got sections in 14.3 for the wall reinforcement requirements. A couple of things you're going to find in there are minimum reinforcement for the ratios. So you've got that, and then you're going to have some thickness of the wall requirements, so how the proportioning and the cover of that wall, and then also some maximum spacing going to be in 14.3.5. Other things you might find in here is going to be the shear. Okay, so we're using our shear wall. These are shear walls most times, our concrete walls. We have the ability to use them as obviously as axial loads, but a big part of concrete shear wall is going to be shear wall design. So we're going to be applying some of these shear reinforcement requirements here in the 11.98 and 11.99. As we go more into the code, we have something that is going to be required for all concrete walls, which is P delta. We talk a lot about P delta going forward in the concrete design, but we also now are talking a lot more in steel. But concrete's kind of always had P delta going in the codes. But what is important to talk about is what the code is requiring. So if we look at section 10.10.2, it says that the design shall be based on factored forces and moments from second-order analysis satisfying three sections of the code. And actually, there's an OR statement. So it's 10.10.3, 10.10.4, or 10.10.5. So it's interesting that what it requires here is that as you either do a nonlinear second-order analysis, it allows you to do either that or an elastic second-order analysis. And then we have the moment magnification. So when we refer to P delta, or what we call something more like what we call big P delta effects, that would be what we would say here is that elastic second order analysis, satisfying that 10.10.4. The other part of the code, actually, 10.10.4 refers to the little P delta as well, requiring that as well. So, and we do that portion of it using this moment magnification. So you've got you're satisfying the PCI requirements, the ACI requirements of the P delta by doing both these methods here. To talk about how that gets applied in Risa, because it's important that you understand how it is applied. When the wall here we see is actually have some loads applied onto it. And we see there's axial loads and lateral loads. The load gets transferred to the wall, and the wall deflects. So that's kind of a theory here where we see on the picture on the right that this wall actually has a little bit of a deflection to it. And in that deflection, we can see here there's an actual deflection calculation, what we call here this delta, and that's basically the measurement of where that end coordinate here, that corner node, was when it started versus where it ended, and that's your delta. That's actually where P delta comes into effect, the name there. But what happens is the deflections induce secondary moments due to the fact that the wall is no longer collinear. So by understanding this actual behavior, what we try to do to resolve that moment there is we apply some shears to the top and the bottom of the wall. And those secondary shears are calculated by using the axial force, the P, times the delta that is found after one solution. We find a delta or a deflection distance, and then we divide that by the height of the wall. So you've got that calculation, and that's what we're finding, that shear, and that's applied to the bottom and the top of the walls. For a single-story wall, you're effectively just getting that top force there. So that's happening inside, and that's what we call that big P delta. Another term we said before was elastic second-order analysis, and you can see kind of different ways that its terminology is used there. We've got the way to do that inside of Risa 3D is that we turn on the P delta check for all load combinations. The program's actually going to warn you if you don't do that, but you want to go into your load combination spreadsheet, and we see that there's a P delta column right there in the middle, and you can say either type a yes or Y, or you actually can open the dialog and tell the program yes to do it for all members. Okay, so it's required there for all the members. And it will automatically do that for you. Now, the little P delta effect is the curvature that's happening. So you've got this big P delta that we talked about here, this delta, which is that corner node and its distance of deflection from its original location. But you also have what we have termed also an element curvature effect. Or if you look at this right side of this wall, see how it's actually kind of deflecting around where its normal, its original location would have been a linear line, but there's a curvature happening. And that little P delta effect there is trying to be accounting for several different things. We try to account for the influence of axial loads, some of the cracking, some of the effects of the load duration, and all that was what we term the little P delta effects, or minor effects that are happening. So they're not going to be, this is, you can tell just even this picture, they're going to be much more minor compared to this big P delta. But the way we do that, we only actually do that for slender walls. That's the most important piece too, is that the code requires this for slender walls. So first they're going to go through a check in here and check if it is slender. So the first thing you do is check the slenderness ratio, which is KLU over R, less than or equal to 22. LU is an important thing to be defined. It's going to be the height of the wall. However, if you do have diaphragms defined, that's actually going to break up into segments. So there's no, in member design, we actually go in and we can figure out what the LU, the effective length is. In walls, we're going to assume that if there's it's going to be the full height of the wall, or if you have diaphragms breaking it up, that's going to help break your LU up there. So if it is slender, or if it is not slender, we're going to determine that. And if it's not slender, then we're not going to assume any P delta effects are happening, little P delta, excuse me. Important to note, it's only the little P delta we're talking about right now. The big P delta, if it is yes to this, then we are going to do some moment magnification. And that's going to happen per section 10.10.6. We're going to go through a whole series of equations that you'll find there. 10.10.6 is going to do a kind of a delta that's going to change the actual moment. And inside of that, you're going to find that it's actually going to change the stiffness slightly. Where we've found this here, EI, found by using from the commentary, where we get that change stiffness. We also have some limitations in there, so meaning that there's some minimum moments that you have to hit in order to do that magnification. So we're going to actually check that, make sure you get to minimum levels, and apply that minimum there. So all of that's going to account for your little P delta. The other piece that's we're talking about now, also stiffness, we're going to talk about crack sections. So in your walls, we're going to want to apply some maybe crack sections in there for your deflection calculations. That's the only place where it's actually your crack sections is going to be applied, is changing actually the moment of inertia there to be for cracked. We can use gross or for the cracked. And if you turn that on, that's actually found inside of the global parameters under the concrete tab. There's a check use crack sections. And you see right there that you can actually just turn it on, and once you do turn that on, it's going to be applied to actually all members, beams, columns, walls, but in particular for walls, there is a assumption there, alpha 10.10.4.1. We assume that for in-plane cracked sections, we are using 0.7 of the gross, and then we're using for out-of-plane 0.35 of the cracked section. So uncracked and cracked for the gross there. So you've got that is your assumption. But if you wanted to change that, if you want to override that, you can open up any of the wall panel spreadsheets in there, and you'll find that under the Advanced tab, you can actually type this in. It's blank, and then when we open up the program, we can see that it actually tells you at the bottom of the screen what it's defaulting to, but it'll be in plane and out of plane. These are the defaults if you want to override. So that's your crack sections, but let's, and we've kind of gone through a lot of the theory stuff inside of there, but now I want to talk about actually modeling the actual, walls inside of Risa. So we're looking at a three-dimensional model here, but let's talk about the nitty-gritty of how to do the walls. So first thing here, I'm going to jump to the next slide, we have lots of types of loading on walls. Any type of load you really can do on a member, you can do on a wall. You can do point loads, distributed loads, surface loads. Those surface loads actually can be tapered. So if you needed to do some tapering, maybe some wall soil pressures, things like that, even hydraulic pressure, you can actually taper that on the surface. So you have some flexibility on the loading. You can also, we're going to be seeing loads in plane, so we can see axial loads in here, or we're seeing loads in plane as if we were distributing it as a shear wall in plane, but we can also load it out of plane. Now, why I make mention to in-plane and out-of-plane is because that's what we're going to see throughout the program. We're going to be putting loads into the program, and we're going to be seeing results coming out as in-plane results and out-of-plane results. So don't forget you have kind of two types of things that you want to see when we review the results. The other piece here is we're going to be talking about the design rules. So in this latest version, we used to have something called just design rules, but what you'll notice here on the top right corner, we have something called wall design rules now. We broke out member and walls, so it's kind of a little bit separate and a little bit easier to understand which ones apply to what. But you've got wall design rules here, and what we're going to be defining here is our concrete cover and our concrete rebar. And so when we open up the program, we're going to first look at our our cover is our first one we'll look at here. And our cover tab here has a couple different things. It's going to just be a typical label is the first thing. You can label that anything you want, and we'll see how that becomes important when we look at a multi-story model. But our outer bars are just defined as either vertical, which you can see here in this picture. The bars are actually going to be on the outside face, coming here, interior and exterior face, either going to be the vertical bars first or the horizontal bars. So you'll notice that it does affect the way the D is measured. So the D is actually going to be a little different whether you pull that bar interior or exterior. So however you're going to be modeling that, if you're doing each face, that's important for each face. If you're doing centered, actually, then it would be, actually doesn't matter here. You can see we're just lining it up in the center. Your horizontal and your vertical bars are going to be centered. You can also define your cover. So it's important to note that you can have different cover for interior and exterior cover. And we can see here in this picture below, I have 1 inch of cover on the interior face, and I have a different cover, a 3-inch cover on the exterior face. So that allows you here to switch up your cover. The edge cover here is going to be showing here on the right. That's showing me that 2 inches, what your distance on the edge should be, and you can change that value. And then we have something here where we just define here the bars that are centered. This is the extra bars. So a lot of times you're going to have a wall that just doesn't work out exactly the way you want the bars to fit, and you might have a little bit extra. So how do we calculate that extra? So Risa is going to come in here, and it's going to say that the wall length is going to be divided by whatever the required spacing is, and we're going to find a spacing for you. We're going to get that extra there by getting that remainder divided by 2. So it's going to be, we're going to basically split out the extra piece on that other side, on both sides for you, and give you that value. Now the only time when that we can see this one's 3.62, so I had some sort of an odd spacing and I had a little bit left over on the edges. Everything else is standard spacing. But the only time that that might not happen, where you might have even a different situation, is when you have real small walls. So if I look at this picture, this is just, I tried to draw a real small, maybe a 12-inch wall. And I actually had only 2 bars were required, and they can't fit in this spacing. So maybe, I had, it was required even on 18-inch, but I only had a 12-inch wall. So what will happen is, if this one is required for each face, I put in here 2 on each side, and really what we're retaining is the cover side. So we want to make sure we get enough for your cover on both sides, and then we're just going to put whatever else fits inside there. So a small wall is kind of an odd case where that might happen. Typically you're going to have it where it's going to be the whole wall length divided by the spacing and that little remainder there. The other big piece that happened inside of the new walls is that when I talked about earlier that you can do different cover for interior and exterior, you now need to know which is your interior and exterior. So we're going to see color coding. We're going to see that you have the interior is going to be in a light gray, and we denote that by a -Z. That little z is a local axis denotion there, so it shows us that that's the interior. The exterior is in a dark gray. So this will really help, first of all, when we're modeling to understand which is our interior and exterior, but also when we're picking up a model and trying to understand what the reinforcement is. You can actually do things like flip that axis. We have a new tool that it has here in the Modify Wall panels that allows us to flip that. So if I draw this incorrectly, which 9 times out of 10 I do kind of forget which way I'm drawing, and when I look at the picture I can say, oh, okay, that's the wrong direction, and what I'll do is I'll open up this tool and I'll flip it for myself. And we'll see an example of that coming in the next couple models here. So let's see Risa in action. Let's actually see how a wall works. So I'm going to open up Risa 3D, as everyone should see Risa 3D right now. What I try to do in here is just open up a sample model, just a simple little wall. We can see a couple different things. It's just rendered. If we look at it in 3 dimensions, it's actually, let me clear the results here so we can just see this wall by itself. It's a 10-inch thick wall. I opened up the data entry look on the wall panel spreadsheet to learn a little bit more about this wall. It's concrete. Its material set is 4,000 normal weight. You can define any thickness. I just chose 10 inches, but we can make it as thin or thick as we need it to be. And right now it's following the design rule of typical. So I'm going to open up my, let me look at my loading a little bit here, and we can see if I turn on this loads a little bit, we can see all the different loading I have on this model. So I have a dead load just applied as a single distributed load on the top. I can apply that along the entire top of the wall. I have some live load, same thing, kind of a distributed load there. I put in some wind load in, and I put actually the wind load out of plane. This is what I defined as the wind load in the Z direction. So it's actually in the Z direction there. I gave myself some wind load in the X direction, which is going to be applied actually as point loads. Try to give you an example of maybe you have some things tying in. I had maybe beams tying in. If I actually didn't want point loads, I could have just tied in beams directly to the wall, and it would have worked as well like that. So I don't have to do just loading. I can put frame members into the wall, and they will accept that as well. This is just sort of a one wall, easy for me to show you a little bit quicker. And we've got the earthquake load applied as a distributed load along the top and as more of a shear load. So with all of that, we've got, if we look at our data entry toolbar here, I'm going to open up my load combination spreadsheet, and I can see I have all my different load combinations in my LRFD here. I've got some service stuff here, but what I'm going to run in my ACI combinations, I want to make sure that all my yes for P delta is turned on, which it is. So I have that all turned on, and I'm going to solve the batch solution. So it's important to run the batch solution. If I ran one single combination, I'm not going to get the full idea of what's happening. Now, a batch solution is kind of an important piece to talk about when we talk about for concrete. A batch solution is going to give me the ability to really investigate using my detail report. A batch will run every single combination, and it will design for every single combination and allow me to investigate with the detail report. An envelope will also do that, but it is going to give me the maximum and minimums in all my reports, where the batch is going to give me a little bit more detailed information. So I recommend for walls designed for concrete to run your batch solution. So I'm going to close that up here, and we're going to take a look at some of our results. first of all, let's just take a look at our joint reactions for a second. So each one of my load combinations got run, and it gives me one wall panel joint reaction result. So I can see I have 80 kips, I have 155 kips coming in for wall panel 2, load combination 2, wall panel 1, load combination 2. And so I see all just but one joint reaction there for each wall, for each load combination. Now, that's interesting because if I looked at this wall, this actually has a continuous boundary condition. So I can tell that by that big solid bar at the bottom. So that's a continuous boundary condition, and I only get one joint reaction. Behind this model is really a finite element model of plates. And so if I open up my plot options, I'm just going to show you how displaying those plates by showing the mesh. And there's a sub-mesh of plates behind there. And so you can see that's automatically all done for you. So the way that size of those plates are controlled off of our global parameters. So if you're not familiar with walls, we have under solution, under global parameters, we have wall submesh size. So right now, the maximum size of that plate element that we have automatically meshed in there is going to be 12 inches. You can adjust that, but a 12 inches is a pretty good mesh size for my model. But you've got here that 12 inches automatically. And my joint reactions, as we go back to that was the point we only saw one reaction for the whole thing. What we're doing internally, though, is if I come back into my plot options, internally, each joint under that plate is actually getting a reaction. So if I show my reactions for each of those, I can show it like this, and we can zoom in a little bit, and I can see that every time a plate element gets tied to the boundary condition, I get a reaction. So what happens is there's a summation of all these forces at the bottom of this wall panel. And the summation is what gives us that joint reaction, that 180 kips for the wall panel 1 for load combination 1. So if we added all that up together, we would get this number right here. And a way we can even verify that too is by using our internal summation tool. That's right here on the left side of our screen. If I click on that internal summation tool, that allows me to cut a plane through this model. I can click on any actual node location to cut a plane. And I can slide this up and down and see what the forces are along there. If we look at the bottom of my screen while I'm doing this, you can see it's fluctuating. And if I scroll way to the bottom, I see that 80 kips, 80.5 kips that was reported there. So that's what I was actually doing the summation along that. We're cutting this internal plane, and we're summating the forces around that. So you can do that internal summation tool if you're familiar with that for any members or plates. That also works here, and that's what we're doing internally. So I'm going to right-click, and actually, let me show you. Let me finish that step 1 there, right there, so you can see what that internal summation tool gives you. Gives you that 80 kips, and 80.5 kips roughly, right at the bottom of that model there. So I'm going to say OK. Okay, so we've got that all displayed here, and that's your joint reactions. The other pieces of information you can get off of this wall is we can look at the wall panel design spreadsheet, and that will give us a little bit more information about what the region is. There's one region in this wall, again, it says a maximum unity check. The shear unity check tells us the load combination that was governing for that, what our PN or MNs are. We can see our concrete. These are unity checks. So this might be very similar to what you would look at when you're looking at your design results. If you had members in your model, it gives you your maximums, it gives you your allowables or your capacity levels here, and you can see a little bit more. But what is more interesting to me is the detail report. That gives us a little bit more information just of the maximum unity check. So I'm going to close that out. I'm going to click on the detail button. That's on the left side of my screen. If I click on the detail button, it changes my mouse a little bit, and I can click on the actual wall. And this will give me a real breakdown of what's happening in the wall. First of all, it gives me an information about what was used in the wall. So we have the code that we use, the 31808. It tells us that we're putting our reinforcement on each face, what the vertical bars are going to be on the outer bars. The number 6s are going to be vertical, horizontal, and number 4s. We see that in the picture with the actual spacing that was called out. So we have number 4s at 18 on center each face, and number 6s at 18 on center each face. So we see that drawn in there. We also get to see the materials that we used. It tells us all the information about the height of the wall, the cover information. So this is all kind of what we call the echo of the input. This is all stuff you should know because you put it into the model right there before we got started. At the very bottom, this explains again what the region, each one of these unity check maximums were. So we have the maximum of the shear check. This also gives us the delta max, so that's going to be our deflection there. We have a delta in plane, our maximum deflection in plane, and our maximum deflection out of plane. The delta is going to be referring to where the plane, where the node was and where it ended up. That's the maximum delta. So almost kind of what we would call like a story drift type of deflection report, where we get an actual maximum location of deflection or maximum deflection there. So that's our wall report. Now that's kind of basic again too, just an overview of what happened in this wall. The more and more detailed you want to get, you can go into your region. Now that region, this is one region in this wall, and so we're going to go to the region report, and it's going to show me region 1, the only region in this wall. And again, it gives me very similar information on the top. If we scroll down a little bit, we see here an envelope diagram. So the envelope diagrams are going to be your axial, your shear, and your moment diagrams. Now these diagrams are going to be maximum for every single combination we ran. Note the word envelope. So it's going to be for the maximum shear that was found. This may not be the same load combination that was found, the maximum axial versus the maximum shear. It might have been a different load combination that gave me moment. So you want to be able to look into more detail. You're going to want to look over to the right, and it will tell you that the governing PU here was for governing load combination 7, okay, and we have 72 kips. And if we look down below that, we can see here that our actual moment and our shear here is listed out actually the same load combination for our model, which is because it's a pretty simple model. So we have, if we're seeing another governing shear there, load combination 7. And as we scroll down below that, we can see here the deflection. So this is an interesting thing here. The maximum governing location for load combination for our deflection is 6. It's not the same load combination as before. So something might be happening that causes a little bit more deflection. We've got here all the different requirements of the steel. We see the wall section properties. We see when it was cracked, area steel provided, what was the row provided, the area steel minimums provided there. Below that, we get to slenderness, bending, span results. So this is where your little p delta stuff comes in. We can see here there's a delta NS. That's actually, this is not going to be slender, so we're not applying this at all. We're going to see a lot of NAs in this wall, but if we had anything where we would see it go to slender. We have in-plane wall interaction diagrams. So we've got abilities here to give you this this P versus M interaction, and we're going to get those values listed there. And then below that, you're going to see the cross-section. And now this is going to be like more of the detailing of what you're doing for your model. So we've got the interior and the exterior face, and then this is as if we're looking down on that 10-inch wall. We can see what the cover was. And this is that little extra we saw. Remember, I explained that earlier. So this is all our in-plane results. Now that's all for a shear wall in plane. But now out of plane is the other piece of this. Remember, we had talked about all your results you want to review in plane and out of plane. So if I go to the out of plane results, I'm going to jump to the out of plane results, I see very similar information, but as I scroll down, some of the things that are going to be different is that I'm going to have actual display here of moment in plane versus interior versus exterior. Because we're now thinking about the model as we were looking into the wall or out of plane. So what our wind was, this is our wind case actually. So we're going to see here moments in the positive and in the negative direction coming in for our both faces. We also see here we've got our same information with our shear details, our deflection details, and as we scroll down we get very, very similar information. Now out of plane becomes where slenderness issues become much more important. We're going to probably see a lot more of the little P delta stuff, even the big P delta stuff come into play when we're out of plane. In plane concrete shear walls are really just very, very stiff, but out of plane they're not as stiff comparatively. We see here that we have two interaction diagrams, one for the interior face of reinforcement, one for the exterior face of reinforcement, separated there, slightly different. If you'll note that those are actually a little bit different because I put the covers in different directions, and I put the cover on one side I have 2.5 inch cover, and the other side I only have 1 inch cover. So that means that the D is actually calculated a little bit differently for each side of the wall. So you're going to have a little bit of a different interaction diagram there. Okay, so if I close the detail report, now I would recommend, I would print all these out. You might wonder, hey, how come you guys always put all that echo information on each single one? Well, if I'm printing these out, I'd like to see all of this laid out for me on each single page. So I do recommend, if you're looking at this level of stuff, you probably print this out and examine it even farther. So you've got that. You've also got, that's your wall panel results. We also have, we can just see a quick, what was the concrete reinforcing on this wall in a spreadsheet format. If I look at the concrete wall, I have it, it just tells me number 4 is at 18 or number 6 is at 18. So that's easy way to look at the model. I'm going to take off some of this information here. The other way we can do looking at the walls, just like we will look at plates, we can look at our panel information on a contour basis. So I can go to the color fills and I can go to contours. I have all sorts of controls for this, just like I would in a normal situation with a plate model, but I can look at maybe FXY here. So I'm looking at, the loading. I'm going to turn my loading off, but I'm looking at the XY kips per foot. Okay, so you've got that listed in contours, and it shows you a little bit of description. But you can turn on any different contour display. Now the contours are important because this is actually all, if you'll note, this is the little axis, the local axis, excuse me, not your global axis when we're looking at this. So when we look at, this is the wall plane X at kips per foot, and we can display what our local axis is by actually showing that right on our wall. Excuse me. So I can see my local axis is my X direction is like this. And then if I wanted to show those contours here, I'm going to just show, oops, excuse me, I lost my screen for a second. But I can show my contours in there as a FX, and I can see that that's in the local X direction. So it gives me the ability to just kind of work with that. Now this is your single wall panel results. We've gone through a lot of different single wall information. Now I kind of want to show you what it looks like to go into a full three-dimensional model. So we can do that in Risa 3D, but I also, what makes it really easy is to go right into Risa Floor. So I'm going to jump back here for a second, and I'm going to close Risa 3D, and we're going to open up Risa Floor. Risa Floor, I have a three-dimensional model with multiple stories. It will help us really to build this model because we can lay out floor by floor. We can put on our walls and our columns in and our beams really fast into this model. And just a second to open up here. But once I have it open, we'll see that I'm going to be building a basement level with multiple levels on top of it. And I have one started for us, so we can just examine that. And here it comes in. Just takes a sec here. Okay. So I'm going to clear the results, so we'll start from scratch and just looking at this model. And what we've got here is a three-dimensional model here. It's just going to be looking at a building model in particular. We've got actually walls along the exterior. We have some shear walls there. We have a core elevator wall in the middle. If we look at this in 3 dimensions, it's just, we can rotate it a little bit to see. I got a really long basement wall in the very bottom. I also here, if we look at, let's just look at that basement. So when you're in Risa Floor, if you're not familiar with Risa Floor, there is a diaphragm at each level. We can either put rigid or flexible diaphragms in. My model is a concrete model. I'm going to assume it's going to be a rigid diaphragm in here. We can also do, we can see here I can do any kind of columns. My walls in particular are red. The difference in color when you're in Risa Floor, red means it's going to be lateral, so we're going to take that into Risa 3D. Blue means it's going to be gravity, so it's going to be left here in Risa Floor. So we'll see if I double-click on any of these walls, I'm going to see that this is my wall panel editor, and it comes in with a lot of the information here, the material, the design rules, and all the information about that wall. I'm going to close that down for a second, and let's open up our wall design rules. This is a really good example of why we would want to have different design rules. My basement walls are going to actually have different reinforcement than my upper and my core walls. And what I did in this model is my core walls are 10-inch walls, while my exterior walls are going to be 12-inch walls. So that means that I really do need to vary their cover based on what they are. So the core walls actually are going to have centered reinforcement, while the exterior walls, which are the basement and the upper walls, are going to be having different cover here on each face. And we're going to tell the program a little bit differently about what cover they need to have. So I would define each wall with its cover information. And I'm going to close that down here, and we can take a look. Each one tells us, if I display, I can display the design rule for each one. So it tells me it's a basement wall here along the exterior and the upper walls here. And I can kind of scroll in, and I see that then now I get sort of that upper wall behavior there. Okay, so you can open up your wall panel spreadsheet. I'm going to open up the wall panel spreadsheet, and I can see in here that I can adjust any of the information right here in the spreadsheet. So I do see 10 inches in there for most of my walls here, or for the inside walls, and I see 12 inches for the exterior walls. I can change the material. I'm using 4,000 normal weight, but you can go up beyond that just by creating an additional types of concrete materials right inside of your material spreadsheet. That's where it comes in from. Again, we said we can do any thickness of the wall there, and so we've got it all laid out for us. So once we've got that all in place, what I'm going to do is I'm going to run this whole model. I'm running through all the load combinations. I'm distributing the loads on this. There's area loads behind there, and I'm going to zoom in a little bit, and I can see that each one of my concrete beams got designed. Let's take a look at what my walls are. So I'm going to look at a detail report of these walls, and we can see here this gives me the wall reinforcement for this whole stack. We see it's now actually not just a single wall, it actually has a stack on there. So we actually get all the reinforcement for that entire stack, and I have regions all designed in there. We can see the same type of region information. Now this is just the axial loads in Risa Floor, so we're not designing for moment, and it gives me a little warning here that it is not doing the moments calculations. It's just the axial, because we're just carrying the gravity loads here in Risa Floor. So I've got all the information just for my gravity loads. Now, the important thing I note here is that I did things a little bit differently in here. I actually did, I have a basement wall split out a little bit differently for the reason that we see that stack. So if I double click on that basement wall, it's a bigger wall here. And if I wanted all of the upper reinforcement for this entire upper portion to be similar. So I actually drew it in as two separate walls. I did that kind of on all of these walls here, so you can see I have basement up to the third floor, and then on the very basement level, I actually keep those walls as just single walls. That allows me to change my reinforcement. So internally, it's going to be submeshed as plates, and they're all going to connect forces, and things are going to be just as if they were one single wall stacked on top of each other. But reinforcement-wise, I'm going to be able to have different reinforcement on the lower levels. So on these lower levels down here, I actually get different reinforcement because I broke them out as separate walls. Now this one I would kind of have to because it's so long. But the other ones down here, this is a separate wall. And we'll see that in Risa 3D when we get there. A little bit easier to see that in Risa 3D. So one of the things you have here in Risa Floor, once you're finished with your design, this is only my gravity design, as I mentioned, but I do have ability to take a look at some of my wall forces, so I can see what the maximum base reactions were, and this is going to be for your gravity design there. You get the maximum base reactions. It breaks it out a little bit, telling me what the dead load was, what part of that was part of the live load. If there was any reduction in the live load, it will give me some of that. So this helps me to see what the wall forces were. I also see the concrete reinforcing, so I can see what happened in here in each one of these walls. Oops, excuse me, that's for my beams, but if I jump over to the walls, it'll tell me a little bit more about each one of the walls, how the reinforcement was in there for the gravity loads. And then I can take this model here, all the information I have here into Risa 3D for lateral design. So I'm going to use the director button on the top right corner. And what it's going to do is going to automatically load my model for wind loads and for seismic loads. Starting out with wind loads, which is really cool, is I can tell the program that I only have wind loads from 10 feet and above, because that basement level is not getting wind loads. So I can tell it, start the base elevation at 10 feet. That means that that sub-level is not going to have the wind load. I set up all my parameters in here, and then I calculate the loads, and what I can see is that the program will go through and it will use the ACI 705, the code I've selected. It'll give me all the different categories and factors that go into that. And then below that, each diaphragm is going to get a load in there. So we're going to calculate the windward and the leeward direction forces, and we're going to apply that in at each floor. So floor 1, 2, and 3 get that. The basement level did not, because we told it it was not part of that. So we're going to see forces in the X and the Z direction. And I'm going to say OK. And the same thing I'm going to do for seismic. Now, seismic doesn't get that, that pass on the 10 feet base elevation, because it's based on your weight, right? So you don't actually get to say it's taken out of the model. But you're going to want to put in your SD1, SDS, S1, all of the information. I used an R of 4 for this model. And I can scroll down here, and I can see that on this model, it gives me my base shear, 341 in each direction. I've got here seismic generation. It's going to generate the forces in the X and the Z direction, and which gives me the center of gravity and applies it right in the X and the Z direction. Okay, so you've got a list of all of that in the model here, and we're going to say OK. And when I come over to Risa 3D, this would be just as if I had built this in Risa 3D by itself. Had I built a model like this in Risa 3D, I would have needed to make sure I put in some diaphragms, because they're coming across in here. So I do have some diaphragms in this model from the floor levels. But if I also have in here, we can see, like I said, I have a separate wall panel. So I have a stack above there, and I have a separate one below on each of these floor levels. Now these nodes in the middle, those are the nodes that are going to be our lateral nodes, but let's just take a quick peek at what our dead loads were. So if I was going to build this model and just design a lateral system, I would need to make sure I did account for some dead load and live load. So if I zoom in a little bit, everything that came over from Risa Floor has this dead load and live load. So it automatically brings all those forces in for us. These were the beams framing in. Okay, we can see those point loads are the beams framing in. We've got some live loads. Again, it's similar live loads in here. And then if we scroll down below that, we see our wind loads in the X direction. So this was just calculated for us, those loads there. I'm going to turn off my project grid, because it might be a little bit easier to see without that project grid. Okay, there we go. So I can see that I've got loads in the X direction. I've got loads in the Z direction. They're coming in on that model there. And they're kind of going into the middle of space. So you may wonder, how are they actually being distributed? Well, you remember we did just say there was a diaphragm at each level. So that is actually going to be applied into the diaphragm at each level there. You can see we've got wind loads in all sorts of directions. We even have partial wind loads. So it helps account for that partial there. And so we have earthquake in the X and the Z directions. Earthquake for this model is going to be what governs, right? Because it's a pretty heavy model. Wind's probably not going to be controlling much in this model. But it's going to be my Z direction, my X direction, earthquake, maybe with eccentricity. I've got all sorts of stuff in there. I'm going to solve this model. So if I'm going to open up my load combination spreadsheet. And I'm going to take a look in here. Again, we have our P delta turned on, very important. We've got all the different kinds of load combinations. I use the load combination generator to generate these loads. So one of the things you'll notice I have in here is I have wind load in the X and the Z direction. But I'm going to click on that quickly. A load combination generator, so you can see. I use the wind load tool here, and I use this X and Z direction. You can even go up to eccentric with quartering. So you'll get all sorts of stuff, and I do recommend that if you're going to run the combinations. Seismic has a lot more options you can add with X and Z. I went ahead and included my EV vertical there, so you can see that's the SDS times the dead load application, so I increase that. We can do non-orthogonal loading on there, and you can do all sorts of overstrength loading on there. Okay, so you can go way more in depth in your load combinations. I want to make sure that we get to run this a little bit. So I'm going to solve it. I'm going to solve the batch solution. Again, the batch solution was what I recommend, using that as you're running this analysis, so we get the detail report. It's going to run through all of these different load combinations. Now, in a Risa 3D model with a lot of different walls, you're going to see run times of just a slighter, smaller, longer time here. We've broken submesh these plates into elements, so you've got a lot of plates behind the scenes. That may be something you want to control in a real large model. This model is not super large, but like I said, you could go to your Solutions tab and maybe increase that mesh size. If you're looking at something real small, maybe you want to decrease that mesh size so you can get actually a little bit better results and tighter mesh, but you're going to see runtime increase from there. So it is something you want to be careful about. Okay, so one of the things we did do is we talked about the solution, and I want to just make sure I have this all properly done, and one of the things I want to do is just render it real quick. We looked at this model earlier. We saw that you have different color codings based on what's the interior and the exterior. Well, if you're looking at my model, you might notice is that that's not the right direction, right? That is showing it as if this is the exterior of my model, and the outside should be actually the exterior. So first, we can just see that in the local axis. You can see that the local axis is flipped, and that's just because I drew it sort of wrong when I was drawing it. I drew one in one direction, I drew one in the other direction. So not the end of the world. Maybe I should try to pay attention better when I'm modeling, but the other piece I could do to fix that is just to go in here and just go to the Wall Panels Design button. It's going to clear my results. That's okay, but I can go to the Modify button here, modify the wall panels, and I'm going to say Use Out of Plane Flip. And if I say Apply, it's going to come into here, and I'm going to just color code it one more time because we can see that a little bit easier. And I'm just going to flip it there, and the colors now match there. So I can scroll a little bit better and see here I've got gray, dark gray on the same sides. So now this is my exterior properly. It would also be wise for me to do the other side of this wall, to flip that, right? Because this is correctly on the exterior, but this one is not. So I'm going to do that as well. Okay, so I can come in here and do that. Now, one of the things is important, right? We were talking about why would we do this in Risa Floor, 3D versus Floor. This is all interior, exterior. This is going to be in regards to our out-of-plane reinforcement. So in that case, the only time your out-of-plane reinforcement comes into play is when we're doing lateral loads or things that are going to be affecting that out of plane. So in Risa Floor, we're not going to really know too much about interior, exterior, and really it's going to be where you're going to be concerned is in Risa 3D, whether this happens. So I can just solve the batch one more time and run through it, and now it's going to properly switch those for me so I get the interior and the exterior on the correct side. And then we'll take a look closer at some of the other pieces of information. So once we have this all run, we have a lot of the same options, but one of the nice parts is if you double-click on a wall panel, you can see the reinforcement and how it is designed on that a little bit differently. Like this one, I am using upper walls as my design rules, and I have number 7s at 8. I'll list it all the way up for the outer face there. And if I looked at the lower wall, I'm using number 8. And so that's really the only reason I broke these walls up, is so I could do that. I could force different reinforcement at different levels. Otherwise, there is just that plate model behind, like we said. So you can see that plate model just showing right behind. Oops, there you go. So we can show the mesh, and we can see that it all connects properly just fine. So not a worry. But we can also do is we can show some of our contours, maybe show some of our FX contours. Let's see here. This is just actually for our dead load and live load combination, but you can see how at each floor level some things are changing because that's where our diaphragms are hitting into our model. So another thing you might want to pay attention to is taking a look at the contours of that model. I'm going to go back to wire here, or rendered for a second. In Risa 3D, again, you have all sorts of results that you might want to take a look at. The wall panel design spreadsheet, again, is something that you can quickly look through and make sure you had all of that unity check, shear check all properly done. Looks like most of my walls panels are actually pretty low. We have maybe one or two that are kind of higher being designed, but maybe I can even go ahead and lower my reinforcement. Or maybe some of these walls are a little bit higher. You know, I don't need as many shear walls. That's the kind of thing where you want to start to look at, and that would be where your wall design results would be. Start to see how many walls you might need, if you need more reinforcement, things like that. So we've got the detail report is, again, the best option for kind of fully getting into each wall. Once you get that detail report, then we see the stacked detail report. It gives us a lot more information for each different level, what's happening on that wall. Okay, so I'm going to jump back in here, and we're going to talk a little bit about, let's see here, what's coming next in Risa. Everybody here. So right now we just did shear walls in there. We didn't see any openings yet. Coming in the next version, we're going to see openings in that shear wall. So in version 10.0 of Risa 3D and Risa Floor at 6.0, we're going to see some openings. And that's going to help you maybe in those shear walls and those cores, you can do some opening design there. We also are going to be adding retaining walls right inside of Risa Foundation. You can do some of that retaining wall work right now inside of Risa 3D because we had said you can do some of that tapered loading in there, but we're going to do some automatic Risa retaining walls design for you in Risa Foundation. And that'll be the next version, major version that will be released there.